Hello everyone, welcome to the video lectures of Modi Institute of Technology in association with Rajasthan Technical University. Today we are going to discuss about the basics of quantum mechanics. Before we understand about the quantum mechanics, we should understand what is the difference between the quantum mechanics and the classical mechanics. The classical mechanics, which is already we know that it is a Newtonian mechanics, explain the macroscopic phenomena such as motion of billiards ball and rockets, whereas if we talk about the quantum mechanics is used to explain the microscopic phenomena such as photon atoms, scattering and flow of the electrons in the semiconductors. Quantum mechanics is a collection of postulates based on the huge number of experimental observations. The difference between the classical and the quantum mechanics can be understood by the examining both the classical point of view and the quantum point of view. If we talk about the classical point of view, the Newtonian mechanics, the laws are written in the terms of particle trajectories. The particle is individual mass point object that has a variety of properties that can be measured, which we call observables. The observables specify the state of a particle, position and momentum. Whereas the system is a collection of particles which interacts among themselves via internal forces and can also interact with the outside world via external forces. The state of a system is a collection of a state of a particles that comprises the system. All properties of a particle can be known to the infinite precision in the classical point of view. Quantum particle can act both as particle as well as a wave. Where comes the particle wave duality? In the quantum mechanical state, it is the collection of several possible outcomes of measurement of physical properties. And therefore, in the quantum mechanics language, the probability theory, the random chances is taken. An observer cannot describe a microscopic system without altering some of its properties. Neither one can predict how the state of a system will change. Quantization of energy is yet another property of microscopic particles. One of the most common principle in quantum mechanics is Heisenberg uncertainty principle. According to the uncertainty principle, one cannot unambiguously specify the values of particles' position and its momentum for a microscopic particles. That is, delta x dot delta p is always greater than half of h cross or h by 2 pi. Position and momentum are therefore considered as incompatible variables. The Heisenberg uncertainty principle strikes at the very heart of the classical physics, that is the particle trajectory. Second principle is the correspondence principle. The quantum physics is applied to the macroscopic system. It must reduce to the classical physics. Therefore, the non-classical phenomena such as uncertainty and duality must become undetectable at the microscopic system. Therefore, the Niels Bohr codified this requirement into the correspondence principle, which is shown in this diagram. Now let us talk about the particle and wave duality. The behavior of a microscopic particle is very different from that of the classical particle. In some cases, it starts behaving as a wave, and in some cases, it starts behaving as a particle. In some experiment, it resembles the behavior of classical wave. In other experiment, it behaves as a classical particle. If we talk about the light, it behaves as a particle in some cases, as well as it behaves as a wave in some other different cases. We will talk about it in later slides. If we'll take the examples of wave as a particle, Max Planck worked on black body radiation, in which he assumed that the molecules of a cavity walls describes using a simple oscillator model can only exchange the energy in quantized unit, which means the radiation will be in quantized form as a particle, behaving as a particle. In 1905, Einstein proposed that the energy in an electromagnetic field is not spread out over a spherical wavefront, but instead it localized in individual clamps, which is called a quanta. Each quantum of frequency n travels through space with the speed of light, carrying a discrete amount of energy and momentum, which is called a photon, used to explain the photoelectric effect, later to be confirmed by the X-ray experiment of a Compton. If we talk about particle as a wave, when we do the double slit experiment, in which instead of using a light source we use an electron gun, the electrons are diffracted by the slit and then interfere in the region between the diaphragm and the detector. Now if we talk about the wave as a particle, first phenomena is photoelectric effect. If we see the graph of photoelectric effect between the frequency, incident frequency and the number of electron ejected out, we will see that the intensity has no effect below the threshold frequency to the number of electron ejection, which shows that the number of electrons ejecting from the surface of a metal will only depend on the higher frequencies. Which means that as per the classical theory, for the light as a wave, its energy is proportional to the square of amplitude. For particle, energy is proportional to the frequency. Therefore, Einstein proposed that the light has a particle nature if we talk in the photoelectric effect. The photoelectric effect provides evidence for the particle nature of light. It also provides the evidence for quantization. If light shines on the surface of a metal, there is a point at which electrons are ejected from the metal. The electron will only be ejected once the threshold frequency is reached. Below the threshold frequency, no electrons are ejected. Above the threshold frequency, the number of electrons ejected depend on the intensity, not on the lower side of the threshold frequency. Now we talk about the postulates of quantum mechanics. The first postulate of quantum mechanics is every physical realizable state of the system is described in quantum mechanics by the state function, which is called psi, that contains all accessible physical information about the system in that state, and this function is called the wave function. Physically realizable states that can be studied in laboratories, accessible information, the information we extract from the wave function, state function, function of position, momentum, energy that is spatially localized. Also, if psi1 and psi2 represent two physically realizable states of a system, then the linear combination, as shown in the equation, with C1 and C2 as arbitrary complex constant, represent a third physical realizable state of a system. We should also note that the wave function psi is basically the position and time probability amplitude, and its square will give the probability of having a system in particular state. The second postulate of quantum mechanics is if the system is in quantum state represented by the wave function psi, then the probability is equals to the square of or square of the magnitude of psi. That is a possible measurement at the time t, and the particle will be detected in the infinitesimal volume dv. Therefore, the normalization condition for the wave function is integration of p dv is equals to 1. Limitation of the wave function. Only normalizable wave function can represent a quantum state, and these are only physical admissible functions. State function must be continuous and single valued functions. State function must be smoothly varying function, continuous derivative. It should have a continuous derivative. The third postulates every observable in the quantum mechanics is represented by an operator which is used to obtain physical information about the observable from the state function. For an observable that is represented in classical physics by a function q, the corresponding operator is qxp. Therefore, in the table we shown some operators. The position operator is x, momentum operator is p, which is equals to h cross upon I del upon del x. Similarly, the energy operator. The fourth postulate of quantum mechanics is basically the quantum equation of motion, which is given by Erwin Schrödinger in 1926, as it is shown in the slide, where iota h cross del upon del t is basically the energy, and which equates the kinetic energy plus the potential energy in the form of operator. The time development of a state function of an isolated quantum system is governed by the time independent Schrödinger wave equation, where h is basically the Hamilton, and Hamilton is the energy operator, t is the kinetic energy operator, and v is the potential energy operator. Thank you.